any atom or ion or molecule. So normally either you tell that this is either diamagnetic or paramagnetic. So this is how you tell any atom or ion or molecule. So you never say that an atom or ion or molecule is ferromagnetic. So that is not true. Okay. So ferromagnetism, you cannot say an atom is ferromagnetic. Okay. So an atom can be either paramagnetic or diamagnetic. So that means it has either a positive susceptibility or a negative susceptibility. So, but ferromagnetism is very different. Okay. So never do that. Never say any atom or ion or molecule is ferromagnetic. It can be magnetic. You can say it is magnetic. It has magnetic moment. So if it has partially filled orbitals, so definitely it is magnetic. But you never say it is ferromagnetic. So we discussed different kinds of atoms. So like transition metal ions or atoms, and then this rare earth, so these are the most the atoms which are actually used quite a lot in any magnetic materials. Okay. So of course another question is, so also we discussed that if you take a metal, the behavior is a complex magnetic behavior due to its core electron and conduction electron. So core electron will give rise to diamagnetism. So conductor electron will give rise to dia plus para. Okay. So this is how a metal would behave. So now depending on which contribution is stronger, so metal can be either diamagnetic or paramagnetic. So one interesting question is, like, what happens if you mix, let's say, a diamagnetic material with a diamagnetic material, or a paramagnetic material with another paramagnetic material, or a diamagnetic material with a paramagnetic material. So what happens in that case? So that is very interesting. So I will give you one example, and from that it will be easier to understand this mixing of two different magnetic materials. So what we can achieve with that? So we take an alloy called copper and nickel. So these are the constituent atoms in that alloy. So this is, sometimes it's also called like a solid solution. So in metallurgy or in material science, you will hear a lot about this alloy and solid solutions. And when one looks at these materials, so typically it is defined by, so let's say, yeah, so this is my copper. On this side, I have nickel on this side, and I write here 8% of nickel. So this is, let's say, my 100%. So this is 0. So I can take 1, 2, 3, 4. So something like this. So this is, let's say, 20%. This is 40. This is 60, and this is 80. Okay. So this is like 20% of nickel. So I have, let's let's say when I am here, so I have 100% nickel, and if I am on this side, I have 0% nickel, and in the other sense, so on this side I have 100% copper, so copper will be 100% when I am this side, and copper will be 0% on this side. So this is how typically, so this is called like a phase diagram. So you can plot this weight percent and then different properties on the y-axis. So we are interested in magnetic properties. So if we want to look at the magnetic properties, so you know nickel is ferromagnetic. A bulk nickel is ferromagnetic. So if I take 100% nickel, so it will be ferromagnetic. So I said this region will be ferromagnetic. Now I decrease the weight percent. So I have this alloy copper nickel. So nickel I am decreasing. So not 100%, but I can say 80%, and then keep on decreasing. So what is replacing that nickel? Copper is replacing. And now when we put copper in, so it is still ferromagnetic, but at certain point, so let's say about 65. So when you are at 65, so that means when nickel is 65% and copper will be 35%. So up to that, this material will be, this copper nickel alloy will be still ferromagnetic. So in this region it is ferromagnetic. From 65% nickel to 35% nickel. And when you go below 65%, so when nickel is below 65%, it becomes, so the copper nickel alloy becomes paramagnetic. Okay. So remember, copper is 100% copper is diamagnetic. Okay, and 100% nickel is ferromagnetic. So now we are mixing a ferromagnetic material with a diamagnetic material and making an alloy. And what we observe is up to 65%, the ferromagnetism is dominating and it is still ferromagnet. And when we go below 65%, so it is paramagnetic. So that means somehow the susceptibilities are cancelling out. So now one interesting combination is, so if I put nickel, so let's say if I take nickel 3.7% and copper will be 96.3%. So when I put this amount of copper and nickel and make a solution on an alloy, so I will have the susceptibility tie will be exactly equal to 0. So the magnetism, the susceptibility will cancel out, and I will have a material where susceptibility will be 0. So why it is interesting? Why this material is interesting? Susceptibility is 0. So because when you want to do, let's say, magnetic measurement, so any other substance, okay, so it could be any material, or can be a particle, or can be a powder, or some salt, or some thin film, okay, so there are many different, so any devices you want to measure, their magnetic properties. So that means you want to apply a field and then you want to see how it responds to that field. So in that case, what happens, so you have to put it in some substance, right? You have to take a container in which you can put it. So you cannot just leave it like in a just drop like that and it will measure it. So you have to hold it with something. So that could be a substrate or that could be a holder, like a sample holder. And normally this copper nickel is used as this particular residue is used as a sample holder for magnetic measurement, because this combination, since it has chi is equal to 0, so there is no magnetic contribution from the holder. So when you are measuring some salt or some powder, so you have your holder and then you put the material in, and when you measure the whole thing, right? So you measure the holder plus your sample. So yes, the sample can be your magnetic material, what you are interested in. So when you are doing a magnetic measurement, you measure the whole thing. And if this holder is contributing to your magnetic signal, so you will not able to identify or clearly say how the magnetic behavior of the material is. And that's why it is you want a holder which does not have any magnetic contribution. Okay, so that's why this alloy is a nice example, and you can take that, which can be used for many magnetic measurements. So the bottom line is, basically what you can do is you can tune your magnetic properties. Okay, using combination of atoms. So one is copper, which is diamagnetic, another is nickel, which is ferromagnetic. So I will never say, let's say, as I said in the beginning, nickel atom, I would never say ferromagnetic. So nickel as a material is ferromagnetic. Okay. So when you combine this and make an alloy, so you can get interesting properties. So you can actually tune the susceptibility of the material. So like if you are about this, so the 3.7%, so this is around this point here. Let's say, okay, so 3.7%. So up to this point, so this is my 0. So yeah, so this is percent of 0. So this is y-axis. So this is my 0, and the material will be paramagnetic in this region. So it has positive susceptibility. So it will be ferromagnetic in this region, and if you look at this region, so this small region here, so it is diamagnetic. And exactly at this point, it will have 0 susceptibility. Okay. So this is a nice. So you can, in fact, put impurities, magnetic impurities, in many materials. So you can take. So this is one example of copper nickel. So you can put iron, for example, in some materials. So impurities, and you can achieve a higher magnetization, or you can achieve a lower magnetization. So depending on what kind of application you want. So you can tune the magnetic properties, so saturation, magnetization, the remanence, the coercivity, all this can be actually tuned. So not only that, you may not mix only this diamagnet and ferromagnet, or diamagnet or paramagnet. You can also mix ferromagnet with ferromagnet, like a hard ferromagnet with a soft ferromagnet. That also you can do. So there are many possibilities. So hard ferromagnet plus soft ferromagnet. So we will probably consider a few of the examples when we cover the ferromagnetism part. Okay. So this is all possible by playing with the different combination of materials. Okay, and you can tune the magnetic properties. Okay. So now we move to. Is it clear? This is clear? or if you have any question on this, you can ask. Okay. Yeah. So next we will go to the most interesting part in magnetism, that is ferromagnetism. So far what we have considered is all paramagnetic or diamagnetic, which have some magnetic moment and how they behave or respond to a magnetic field, their susceptibility, and so on. But ferromagnet is very different. So let me take one. So the classic ferromagnetic materials are your iron, cobalt, and nickel. So this is like one of the first or widely used ferromagnetic materials. So I would say like almost 90% of magnetic materials will either have one of these: iron, nickel, or cobalt. Okay, so now let me plot M versus H. So if I take a piece of iron, a piece of cobalt, and a piece of nickel. So this is an experiment, like experimental plot, but I'm plotting here. So this is your iron, and this is around 1700 EMU per centimeter cube. I think this will be, let's say, your cobalt. So I'm not plotting it exactly how it should, so just approximately. And then maybe this one. So this is my nickel. So what you observe is, so in experiments actually, so iron has the highest saturation magnetization. So if I write down the Ms of iron will be greater than Ms of cobalt and will be greater than Ms of nickel. So these are the highest saturation. But cobalt has a higher coercivity. So if you look at the coercivity of cobalt, it is higher than coercivity of iron, or maybe coercivity of nickel. So there are two things here. Okay, so one is the saturation magnetization is different for different materials, and then how they attain saturation. So there are two things involved here. So one is saturation magnetization, so normally it's called MS, or in the book M0 as well. Sometimes it is written like M0. So this is saturation magnetization is different, and how you achieve saturation, so that is also different, because the shape of the curve is different for different materials. Okay, and that's why, like it is definitely a material related property, but we can develop like a theory, uh, one theory which can explain these different behaviors in a one single theory, and that theory was developed by a P.A. Weiss. So it's called Weiss theory of ferromagnetism. Okay. It is called. So it's called Weiss theory ferromagnetism. So this is one of the first theories. So based on just the classical understanding of magnets in those times, so in 1906, so based on the Van Levin theory. So to understand the ferromagnetism, so what Wise suggested, he said, so the first thing is, so there is some kind of, okay, so another interesting comparison was, which I should mention before we go into the theory, that, so if I measure the susceptibility of iron at a particular field, of the, like if I go to 100 oyster or maybe 500 oyster field, so susceptibility will be around 1700 EMU per centimeter cube. And if I take any paramagnet in that comparison, so this is a ferromagnet, so if I measure any paramagnet, so it is of the order of 10 to the power -3 EMU per centimeter cube of this order. So you see the huge difference in the susceptibility of a ferromagnet in comparison to a paramagnet. And how do you justify that, or how do you explain that? So why he did? So he suggested that this ferromagnetic materials, there is some kind of, and in fact, this ferromagnetic materials also have some spontaneous magnetism, right? So ferromagnets have spontaneous magnetization. So that means you have magnetization without any external field. So what does that mean? So he said, like, there might be some field. So we do not know how it is generated or what is the origin of that. But the assumption is there is some magnetic field which is called as molecular field, or it is also called as a mean field, which all the atoms experience in a ferromagnet. So without any external magnetic field, so there is a molecular field or magnetic field or mean field. And what is the order of that? So this is defined as Hm, which is known as gamma into M. So M is your magnetization. So this is your magnetization, and this you can call as molecular field coefficient. Okay, so you can, gamma is the molecular field coefficient and M is magnetization. So all the atoms, magnetic atoms you have in a ferromagnet experience a molecular field Hm, which is proportional to your M. Now the question was, if I take a piece of iron, so it is not magnetic. Only when I bring it close to a magnet, so then it becomes, it is attracted, so it becomes magnetic. So it shows some magnetization. Otherwise, if I just take a piece of iron which is never exposed to any magnet, so it will have a zero magnetization. So how do you explain that? So he suggested, so then he gave this domain theory. Okay, so one is the molecular field, and so this is one, this molecular field, and the second one is the domain theory. So what does this domain theory tell? So like Of course, the magnetic atoms, so your entire magnetic material, so if you take a magnetic material, so it is divided into domains. Okay, so this is your domain. So here we take only two domains. So that means in this domain, all the magnetic atoms are, they feel the molecular field in such a way and they are aligned in this direction. Okay, and then when you go to another domain, all the atoms here, so if I take like atomic moments, so I can say all the atoms would be pointing, magnetic moments would be pointing in this direction here, and here they are all pointing in this direction, in the opposite direction. Yeah, and this is called a domain wall, which separates it. Okay, so you have domain and domain walls. Okay, so it is 8:29, so we have to stop, and we will continue with it in the afternoon session.